Vertical circles, if you're moving in a circle, your velocity, your speed is tangent to the radius in terms of the direction, and you're accelerating inwards. Good example of a vertical circle is a Ferris wheel. Another great example of a vertical circle, you've all done it, is just having a weight on the end of a string and whirling it like this, or maybe you've done it with a bucket of water and always been amazed at how you got to stay dry. Those are great examples of vertical circles. Also, jet planes doing a loop. Good example of a vertical circle. So example 1. A person rides on a Ferris wheel. They sit on a Newton scale, because I want to do everything in newtons instead of kilograms, that measures, what does a scale measure? Normal force. I mentioned that in the question, but I shouldn't have needed to. At the bottom of the Ferris wheel, what does the scale read? Equal to mg? Bigger than mg? Or less than mg? Now, you may be able to kind of guess if you've been on a Ferris wheel that moves fast or some other loop-the-loop ride that moves fast. But I think we can convince ourselves even more by drawing what? I think a good free body diagram. So there's the person at the bottom. What are the forces acting on them? Get the obvious one. What else? There is a normal force pointing which way? In fact, you know what? What path is this person tracing out? Where must the net force be pointing? Toward the? Which means, which force am I going to draw longer? Who's winning? Toward the? Toward the middle. I'm going to draw a normal force. Bigger. The answer here is you're going to feel heavier at the bottom of the loop. You're going to feel heavier at the bottom of the loop. Now, the Ferris wheel at Playland doesn't go very fast, and most Ferris wheels don't go very fast. But there are other rides that go in vertical circles. Only most of the time, you're always facing inwards. There's one called the Enterprise, which is great, but on that one, when you're on the top, your head's pointing down, unlike with a Ferris wheel, when you're on the top, your head is pointing up. But, so as explain your answer using physics principles, I would say this. If we are moving in a circle, the net force must be inwards. The winner must be inwards. When you go winner minus loser, the biggest force is going to be pointing towards the center. In fact, Jeff, if you wanted to write an equation, it would be this minus that equals FC, equals moving in a circle. On a Ferris wheel, I wrote, people feel light at the top and heavy at the bottom. Why does this happen? Well, hopefully I've just convinced you why you feel heavy at the bottom. Your normal force is bigger, because right now, all of you right now, normally you feel mg as your normal force. But in a Ferris wheel, look at my free body diagram, the normal force is bigger at the bottom, bigger than mg. I'd feel heavier. What about at the top? Well, what are the forces acting on this guy at the top? Get the obvious one. What else? Normal force pointing which way? Up this time. Now, what path is this person tracing out? So where must the net force be pointing? Toward the? Which means I know normal force has to be smaller, not bigger. Otherwise, I'd have the net force pointing away from the middle, which is not what's going on. Which means, is your normal force at the top bigger, smaller, or the same size as mg? Look at my picture. Is your normal force at the top bigger, smaller, or the same size as mg? Smaller. Would you feel lighter or heavier at the top? Lighter. That's if your, Carl, head is pointing up. Okay? So why does this happen? There's your free body diagram. It's going to be at the top, winner minus loser equals MAC. If we redid our free body diagram for the bottom, we have gravity. He's moving in a circle, which means my net force has to be pointing inwards. At the bottom, it's winner minus loser equals MAC. By the way, you'll also notice here the masses don't cancel, in that if you're a heavier person, you will feel heavier than if you're a lighter person. It's why kids can handle rides. It's why as you get older, you may not handle rides quite as well as you used to. Sorry. Yeah. Could have gone during lunch. Quick like a bunny, but next time go during lunch. In the previous example, the Ferris wheel is a rigid wheel. The top and the bottom of the wheel will always have the same speed. And that means the circular motion is uniform. We can't analyze it. This is not always true. Consider a pendulum which will move faster at the bottom of its path than the top. Watch. Example 3 says, write force equations for the vertical pendulum at the top of the loop. How will I get the equation, Carl? You know what this is a job for? Yeah. So, at the top, what are the forces acting on it? Get the obvious one. What else? Is it sitting on a surface? You saw me just whirling it around my head. Was it sitting on a surface? So is there a normal force? You know what? The top is tricky. Let's get the bottom one first. What are the forces acting on it? Get the obvious one. What path is it tracing out? So there has to be a force bigger this way. Which force? Tension. The rope. So at the top, not only is gravity tugging down, but there's also another force down. Which force? Tension, like you were just feeling. So at the top, my equation is this. Tension plus mg equals centripetal force, Fc. No loser, it's winner plus winner, because winner is towards the center. At the bottom, who's winning? What path are we tracing out? Where must my winning force be pointing? Toward the center. So the winner is going to be tension, the loser is going to be gravity. If I want to, I can get tension by itself. Usually you'll know the mass. I mean, you could solve for mg, but usually you'll know the mass. So what we're saying is this. In a vertical circle, there can be tangent forces like gravity that speed up or slow down the object. The net force inwards is still MAC, is still mv squared over r, or m4 pi squared r over t squared, and there are no horizontal forces. Remember the horizontal one, the vertical forces were balanced, and there was just a horizontal force inwards. In a vertical circle, it gets a little trickier. Okay. I like example 4, I like example 4, I like example 4. Sure. Looking at example 4, is this a Ferris wheel? Nope. Why? Because at the top, which way is your head pointing? In fact, there is a ride that does this. What, you know what it's called at Playland? Nope. Well, that does a different kind of a loop. The Enterprise. Okay, the Enterprise is it's a big, huge circle. It starts out flat and it raises vertical. And when it's going at its top speed, at the top, your head is, in fact, your head is always pointing towards the center. That's a nice one to analyze, by the way. Okay? So we're talking about that ride. Here's what it says. A 70-kilogram passenger is moving at 10 meters per second at the top of an upside-down roller coaster. Find the force the seat exerts on the person. What force are they really asking me to find? Jake, normal force. You know what there's a job for? What are the forces acting on this person? Get the obvious one. Which way? Yeah. What else? Normal force. Which way? Down. Who's winning? They both are. Who's losing? No one. Now, how do I know which way is the winning direction? What path is this person tracing out? So the net force is always pointing toward the, are you cluing in why I ranted on that? Now I can really analyze some nice stuff. What's my equation going to be then? It's going to be normal plus mg equals MAC. You could write FC, but now we're starting to take some shortcuts a little bit. Which version of centripetal acceleration do they want me to use? The one with the period or the one with the speed? Why? How do I know? Okay, by the way, if you do analyze this right at Playland, you won't know the speed, but you will have timed how long it takes someone to go around once. That's really easy. You just pick somebody, start it when they're at the bottom, stop it when they're at the bottom, and you know the period. So that's why I said the one that I use the most in quote-unquote real life is the 4 pi squared r over t squared. Oh, and then you can also calculate how fast you're traveling because it would be 2 pi r over the period. It's kind of nice to know. Anyways, so I'm going to go with Fn plus mg equals mv squared over r. What did we say this question wanted us to find? Sorry? mv squared over r minus mg, right? Minus the mg over in this case? Okay. Do the masses cancel? No. There's an m and f, there's not an m and fn, so we can't do that. Do I know the mass? Check. Do I know the speed? Check. Do I know the radius? Check. Okay, then it's plug and chug. It's going to be 70 times 10 squared over 8 minus 70. You got 189? 189 what? Okay. What does this person normally feel? That. You would be on this ride scared because you would feel like you were about to fall down. You're not. There is still a normal force there. You are still being pressed into, your inertia is still pushing you into the seat, but that's only at about, what, 1/4 of your normal force, no pun intended, or about 1/3. You would grab the handle, something feels weird, you'd feel lighter. What if we sped you up? If we made your speed faster, would you feel heavier or lighter at the top? Heavier. In fact, you know what? Probably get you feeling so fast that you'd actually not just feel mg, you'd feel more than mg. You'd feel like you were getting pressed out into your seat. And in fact, that's probably what they do on most of these rides. They have a healthy safety margin. So, in the previous example, I asked, what would happen to the scale reading if the roller coaster moved slower or faster? You know what, Ben, there's 2 parts. How about we do that? What's our equation that we derived? We said, well, it turns out in both situations, normal force was mv squared over r minus mg. The normal force was equal to mv squared over r minus mg. I'm going to do this one totally algebraically. Then I'm going to say, okay, Let's do slower first. Now, how would I write slower? I would say as V decreases, there's my abbreviation for slower. What can you tell me? What did you say would happen? If V gets smaller, what's going to happen to the normal force in that equation? Right? Slower you go, the more you feel like you're going to fall. In fact, if V was 0, you're going to fall. In fact, there's probably a speed such that you're still moving, but you're not moving fast enough for anything to be keeping you in your seat, and you're going to fall. Oh, and as V increases, normal force increases. Is that okay, Anthony? Turn the page. So let's look at, and by the way, when someone, I said, what's an example of this? Yes, also roller coaster loops, except in real life, and I'll talk about this, most roller coaster loops aren't loops. We're going to actually crunch the numbers, and the G-forces, if it was a circular loop, are crazy. So most roller coaster loops are built differently. They look like loops, but they're not. It says this: if the pendulum in example 3 or the upside down coaster of example 5 were moving at the minimum safe speed, what would that imply about the forces? Well, the minimum safe speed would be and I'll show you what I mean. So it says, find an expression for the minimum speed at the top of a vertical loop, either for a rope or for a rigid frame roller coaster. Let's do the rope first. What are the forces acting on this mass? Get the obvious one. What else? Okay. I want you to watch something. And for those of you who are really paying attention, I've deliberately made a mistake. So at minimum safe speed for a rope swing, okay, we would get this. First of all, who's winning? They both are. My equation would look like this. Winner plus winner equals mv squared over r. But what did you just tell me if I'm at minimum safe speed? So what I really get is this. mg equals mv squared over r. Now it turns out what happens here. The minimum safe speed is the same no matter what your mass is. It's going to be the same speed for everybody. And it said, get an expression for v. So if I get the v by itself, I think I'm going to get v equals the square root of g. But here's the mistake that I made up here. It's not the normal force that equals mg. It's the centripetal force that equals mg. What that's saying is, oh, there's no other extra forces, which means that normal force that you're used to feeling that holds you in the chair ain't there anymore, or that tension that you're used to feeling, which holds the mass in place through the rope, ain't there anymore. What about here? Well, here I have gravity and normal force. Here I have normal force and mg equals mv squared over r. But Kylie, if you were upside down in that chair and you felt yourself start to fall, the reason you would feel yourself start to fall is you would feel weightless. You would feel that your normal force was equal to what? You're right. Same as that's equal to 0, right? So same as this is equal 0. At minimum safe speed, that equals 0. This equals 0. So what we really again have is and lo and behold, we get the same thing. You want the minimum safe speed for either a roller coaster or a rope swing. It turns out it's the square root of GR. Example 7. If we spin a bucket of water fast enough, it's possible to momentarily invert the bucket and yet not have any water fall out. How many of you have tried this before, either recently or as a kid, right? How many of you have tried slowing down, and seeing just what you can push it to in terms of limit on a hot summer day? If you get splashed, you don't care. I'm the only one? Okay. When I was a little kid, okay, how slow can I go? And all of a sudden it starts to slosh. Maybe I can go a bit slower, and oh, wait a minute, no, some came out, and I got wet. Explain why. Sorry? Why does the water not fall out? As long as V is bigger than that, our equation is going to be, well, what are the forces acting on this water? Get the obvious one. What else? It's in a surface. It's sitting on a surface, so there is a normal force. So as long as I spin faster than whatever g times the radius is square rooted, I'll get normal force plus mg equals mv squared over r. Get the normal force by itself. I'll get normal force equals mv squared over r minus mg. And what that means is, as long as this, oh, I thought I changed colors. As long as that is bigger than mg, I'll get a positive answer. Right? Jeff, as long as this answer is bigger than that, I'll get a positive answer. There's some leftover normal force. There is a force pushing it up, which means it feels like it's being pressed into the bucket. The same way when you feel the chair pushing you up on the elevator, you actually feel like you're getting pushed back down. That's what's holding it in. As long as that is bigger than... Sorry, people at home on the internet are going, huh? As long as this is bigger than that, we're safe. Now, how can I make this smaller? Can I change the radius? No, my arm doesn't get short. I'm maxing my arm out. I can go slower. I can go slower. I can go slower. And eventually there's going to come a speed that's so small that this is smaller than that, which, oh, I don't get a negative normal force. What I have is an unbalanced force. The water's going to accelerate down and land on me. Is that okay? Turn the page. Example 8. You can think of a space station as either a horizontal or a vertical force, because there really, Riley, is no up, down, left, right in space. It's really all relative. So a space station has an outer radius of 140 meters. Check. The station rotates so that the occupants at X on the outer wall experience an acceleration of 9.8 meters per second squared. What acceleration were the occupants at Y experience at the 100 meter radius? Sarah, I'm sensing this has got a two-part question because they gave me two locations. So I think what I'm going to do is I'm going to have at location X at location y. Okay, let's look at location y right there. What are the forces acting on those people? Oh, no, sorry. Don't get the obvious ones. We're in outer space. We did this the other day. Who remembers? What is the force that's actually pushing you in a circle on a space station? And you're moving in a circle, so it's not just MA, it's MAC. Which version do I want to use? The one with the period or the one with the V in it? You know what? I'm not so sure. They didn't give me either. Maybe this is where I got to start going to part X. Well, in location X, it's also going to be now, what is the normal force normally? In fact, Anthony, what we're really saying is I could have skipped this line here and gone straight to, it does say, hey, you know what? On the outside wall, you're experiencing an acceleration of 9.8. I could have gone straight to saying 9.8 equals AC. Who's traveling faster? Y or X? Don't write that down. Who's traveling faster? Y or X? Or are they at the same speed? Have you been on a merry-go-round before? Any of you? So, are you traveling faster on the outside or on the middle, or is it both the same? Darian?
The outside.
You're right. Now, why? Well, do you remember? Speed was 2 pi r over the period. As r gets bigger, what happens to speed? Increases. What about the period? Well, the period is how long it takes to go around once. If it takes these guys 15 seconds to go around once, how long will it take these guys here? Still 15 seconds because they're part of the same disk, which is why they have to be traveling slower, because in 15 seconds they only have to go in that big a circle, where these guys in 15 seconds have to go in that big a circle. The further inwards you are, the slower your speed. Here's what that means, Jordan. These two groups, X and Y, are not traveling at the same speed. But you know what they do have in common? They have the same period. So you know which version of the equation I'm going to use? The one with the T in it. I'm going to say G equals 4 pi squared R over T squared. And over here, I'm going to go MA equals MAC. Mr. Dueck, you said the normal force was ma. Well, really, what the question is asking is what's the acceleration at the 100-meter radius? So I want to find this A, but I know it's being caused by moving in a circle. In fact, I'm going to get 4 pi squared R over T squared. The R's are different, but the periods are the same. I think what I can do here, Tawny, is I can get the period from this, because I know G is 9.8. And once I have the period at location X, I can walk it over, and that'll be the period at location Y, and I can tell you what kind of an acceleration they're feeling at location Y. You okay with that? It's a lot of thinking. I like this question. I like this question. I like this question. Somewhere. I won't necessarily say whether it's on a test or a quiz because I can't remember, to be quite honest. Let's get the T by itself. The period is going to be 4 pi squared R over G. Stuff moves diagonally. Except really that would get the t squared by itself. How to get rid of a squared? The period is going to be the square root of 4 pi squared. Now, r at location x is 140 divided by 9.8. 4 pi squared 140 divided by 9.8 square root. This space station rotates every 23.75 seconds. Which means when you're further in the middle, you'll also be rotating at that same period. Different speed. I can now say A is going to be 4 pi squared. This is A at location y. I'll call it AY. 4 pi squared, R at location y, which is 100, all over 23.75 squared. So cool, in this space station, on the outside edge, it feels like Earth gravity. But as you move towards the center, it's going to feel less and less. At 100 meters, these people feel 4 pi squared r over answer button squared. Oh, they feel exactly 7. You would feel a little bit lighter. In fact, probably what you would feel is like you had extra energy, or you'd feel stronger, you could jump a little higher. You'd feel kind of neat. Wow, everything seems light somehow. At least for a little bit until your body's got used to it. Put a box around that because there's A's kicking around everywhere. Turn the page. One more. I like example 9, I like example 9, I like example 9. Almost certainly it's an amusement park ride. It says the person riding a Ferris wheel, the Ferris wheel is rotating uniformly. It says the centripetal force acting on the person is 45 newtons. Oh, this time they gave me FC. What force does the seat exert on the rider at the top and at the bottom of the ride? What's this question asking me to find? It's asking me to find the normal force in 2 situations. Okay. Let's start. What do you want to start with, top or bottom? Bottom? Bottom's usually a little easier because on the bottom, what are the forces acting on this person? Get the obvious one. What else? Why did I draw the normal force so much bigger? What path is this person tracing out? So where must my winner net force be? Toward the... Okay, so the bottom, I'm going to have this. Winner minus loser equals FC. Now, usually on my next step, I'd replace the FC with m4 pi squared r over t squared or mv squared over r, but they told me what FC is this time. So I'm just going to say the normal force is going to be FC plus mg. You know what? The normal force at the bottom is going to be 45 newtons plus 75 times 9.8. And I get 780 newtons. They're going to feel a little heavier. How much heavier? By 45 newtons, which is not much. By the way, since you know the 45, the centripetal force, If I gave you the radius, you could find the velocity or the period, since you know also know the mass. What about at the top? Okay, what are the forces acting on the top? Get the obvious ones. Gravity. What else? Pointing which way? Is this person's head pointing up or pointing down? Up, so normal force is going to be pointing up. Why did I draw normal force so much smaller than gravity? Which path is this person tracing out? A circle. So where must my net inwards winning force have to be? Pointing toward the center. So who's winning here? Who's losing? At the top, it's going to be gravity minus Fn equals Fc. Hey, we've done this little dance before, Alex. Plus that to there at the same time, minus that to there. We'll get gravity minus Fc equals the normal force. And you can see how similar these two equations are, but why they're different, I hope. The normal force is going to be gravity, 75 times 9.8 minus 45. Right? And I get 690 newtons. I'll feel a little lighter at the top. Vertical circles. What's your homework? Number 1. By the way, part B says, find the speed in which you'll experience. When do you feel weightless? When which force is 0? Don't say gravity. When it says that, what you want to do is do a good free body diagram, but when you go winner minus loop, whatever the heck it ends up being, you can then say, oh, Fn is 0, I'll plug that in for a value. And you should be able to find the speed at which the car drivers, you may have experienced this going over a hill where you have that stomach feeling. In this case, these people would actually, in fact, this car, if it went any faster, would leave the ground, like a ramp. Try number 2. Try number 5. Number 7. Number 9. Number 12. There's only a few there. Okay. I'm going to assign number 8, but number 8, there's a very subtle assumption. I like the physics of number 8, and I do like number 8. I do like number 8, except there's a subtle assumption that we have to make. So many of you, myself included, will do this wrong the first time and then adjust, because I think the question's worded poorly, but I like the jet fighter doing a vertical loop. Speaking of vertical loops,